The directions say to evaluate the surface integral. In example 1, suppose we have the double integral over S of x plus y plus z ds, where S is the parallelogram with parametric equations x equals u plus v, y equals u minus v, and z equals 1 plus 2u plus v. U is greater than or equal to 0 and less than or equal to 2. V is greater than or equal to 0 and less than or equal to 1. All right. So I want to define a vector valued function, r of uv. R of uv is a vector where the first component is u plus v, the second component is u minus v, and the third component is 1 plus 2u plus v. And then I want to look at the partial derivative of r with respect to u. And so to find that, what I'm going to do is take the partial derivative of each component with respect to u. And when I do that, I get the vector 1, 1, 2. And then I'm going to take the partial derivative of r with respect to v. And then to accomplish that goal, I'm going to take the partial derivative of each component with respect to v. And when I do that, I get the vector 1, negative 1, 1. And so from there, I want to calculate RU cross RV. And when I do that, you can see that I get the vector 3, 1, negative 2. Okay. From here, we want to take the magnitude of RU cross RV. And when I do that, I get square root of 14. Now I'm ready to make my substitution. So the double integral over S of x plus y plus z ds is equal to the following. Now, this is all substitution all the time. Remember, when I look at x, x is equal to u plus v. Okay, so again, this is a double integral, right? Y is u minus v. That's right here. And then z is 1 plus 2u plus v. ds gets replaced with square root of 14 dA, but instead of dA, we have du dv. Okay, that's right here. So again, ds got replaced with square root of 14 du dv. Now, the limits on u go from 0 to 2. That's the innermost integral. And the limits on v go from 0 to 1. So that's the outermost integral. And so that's right here. So this is equal to square root of 14 times the double integral, where the limits on u go from 0 to 2, the limits on v go from 0 to 1, and my integrand is 4u plus v plus 1 du dv. So how did I get that? Notice how the v's cancel. And then u plus 2u is equal to 4u. I still have that v there. That's right here. And then I have the 1 over here. That's right here. And so to solve this double integral, what I want to do is I want to integrate with respect to u first. And that's what I do on the next page. So this is square root of 14 times the integral from 0 to 1 of 2u squared plus uv plus u, evaluated from u equals 0 to u equals 2 dv. So I would specify that I'm going from u equals 0 to u equals 2 because a lot of times our integrands are going to contain multiple variables, and it's very helpful to keep track of what variable you're plugging in for. So on the next line, we get square root of 14 times the integral from 0 to 1 of 2 times 2 squared plus 2v plus 2 dv. And this is square root of 14 times the quantity 8v plus v squared plus 2v evaluated from 0 to 1. And so the correct answer here is 11 times the square root of 14. It's very important that it's all substitution all the time. You want to be very careful with your substitutions. Okay, so that's example 1. Let's take a look at example 2. Suppose we have the double integral over s of x squared yz ds, where s is part of the plane z equals 1 plus 2x plus 3y that lies above the rectangle 0, 3 cross 0, 2. Now, we're going to regard x and y as my parameters, and we're going to define our vector valued functions. So we're going to parameterize the surface. And so r of xy is equal to the vector where the first component is x, the second component is y, because remember, x and y are my parameters. And then I'm going to express z as a function of x and y. But notice z is equal to 1 plus 2x plus 3y. So in the third component, I replace z with 1 plus 2x plus 3y. And so that's my vector valued function. So r sub x, the partial derivative of r with respect to x, is equal to the vector 1, 0, 2. The partial derivative of r with respect to y is equal to the vector 0, 1, 3. Rx cross ry, so same pattern, is equal to the vector negative 2, negative 3, 1. And so when I take its magnitude, so the magnitude of Rx cross Ry is equal to the square root of 14. So I just happen to be fortunate in these first two examples that I got square root of 14. Are you always going to get square root of 14? Absolutely not. Is Rx and Ry ever going to be vectors where the components are just numbers? No. It is possible that you can get Rx and Ry where the components are variables. So something to keep in mind. But the pattern will be very similar in how I approach it. So we're ready to make our substitution. So the double integral over s of x squared yz ds is equal to. Now, we have a double integral where our y limits go from 0 to 2, and that's the innermost integral, right? And my x limits go from 0 to 3, so that's the outermost integral. So x squared gets left alone, y gets left alone, and then I'm going to replace z with 1 plus 2x plus 3y. And then I integrate with respect to y first, and then with respect to x. Now, a fair question is that could I have integrated with respect to x first and then with respect to y? And the answer is yes, you can. I claim it would not matter. And then remember, there's a square root of 14 floating on the outside, and then I'm integrating again with respect to y and then with respect to x. So ds got replaced with square root of 14 dy dx. And so this is square root of 14 times the integral from 0 to 3, and followed by the integral from 0 to 2 of x squared y plus 2x cubed y plus 3x squared y squared dy dx. And so what I'm going to do is integrate with respect to y first. And so this is square root of 14 times the integral from 0 to 3 of x squared y squared over 2 plus x cubed y squared plus x squared y cubed evaluated from y equals 0 to y equals 2 dx. And so this is square root of 14 times the integral from 0 to 3 of. Now I'm going to replace the y with 2. And when I do that, I get let's start again. So it's square root of 14 times the integral from 0 to 3 of 2x squared plus 4x cubed plus 8x squared dx. And now I'm in the clear. So in the second line, it's a Calc 1 problem. And then incidentally, when I replace y with 0, I just get 0. So that I'm okay there. And so this is square root of 14 times the quantity 2/3 x cubed plus x to the 4th plus 8/3 x cubed, evaluated from 0 to 3. So this is square root of 14 times the quantity 18 plus 81 plus 72. And so the correct answer for example 2 is 171 times the square root of 14. And that'll do it for this video. It's on surface integrals, and we did 2 examples. Thank you.